Right. Now what will make these equations just a little more challenging than the ones we looked at last time, the earlier equations used a lot of the rules from algebra. Solve by factoring, solve by quadratic formula, you know, gets everything on one side, make it equal to 0, factor out a greatest common factor. These equations may require some type of trig identity in order for you to solve them. So again, as you can see, example 1 will be, we're going to use a half angle identity. We may need to use a double angle identity. We may need to use one of the trig identities in the back cover of your textbook. So example says, solve 2 sine x over 2 equals 1. Part A, give me answers only in this interval. And like I said, part B, here's in a case where they're asking you for all of the solutions, which I have an easier way of coming up with how you're supposed to write that answer. So let's start with the equation. 2 times sine x over 2 equals 1. And let's get the sine of x over 2 all by itself. So there we'll simply divide both sides of the equation by 2. So we get sine of x over 2 equals 1/2. I mean, this is where the textbook says use your half angle identity, and I'm saying, look at this problem saying no, use common sense. You know, why use an identity? If you know that the sine of this angle, you know, treat this whole thing as being an angle. You know, the sine of red rectangle is 1/2, positive 1/2. Well, what 2 angles does red rectangle have to be? Well, what quadrants are we working in? Where the sine's positive, 1 and 2. And what angle gives you a sine of 1/2? 30 degrees. Well, they're specifying radians, so we're going to write that as pi over 6. So we know that x over 2, red rectangle, right? We know that x over 2 is equal to pi over 6. Or what would the quadrant 2 counterpart be? Quadrant 2 would be pi minus pi over 6. So that's 5 pi over 6. So x over 2 has to also equal 5 pi over 6. So we're not quite done. You know, it's x over 2 that has to equal these 2 angles. So let's cross multiply and solve. When we cross multiply, we get 6x equals 2 pi, or 6x equals 10 pi, and then we'll divide both sides by 6. Divide by 6, divide by 6, put our fractions in lowest terms, and we get pi over 3, or divide by 2, 5 pi over 3. So there's your 2 solutions to part A. Nowhere in that did I use a half angle identity. I just think that you're overanalyzing the problem that way. Makes it a little bit more difficult in my opinion. Okay? So those are the 2 angles in the specified domain that solve that equation. Now we're going to open it up to all of the coterminal angles. All angles that terminate or end up in the same location as these 2 angles. And looking at some of the previous problems that we did, an easier way of looking at it is, let's go up here to the original equation. And if we were to focus on writing this as a function, all right, I could take this equation and we can think of that as being f of x is equal to 2 sine x over 2 minus 1. What would the period be? What would the period of this function be? Remember how we found the period? Remember, I call it magnitude, amplitude, period, phase shift, all that kind of stuff. So what value is in the b position with that equation? Well, a is 2. B is, you think of this as being 1/2 x. B is equal to 1/2. And recall with the sine function, period is 2 pi over b. So in this case, it's 2 pi over 1/2, or 4 pi. And there is what you simply add to our two answers to give you all of the other answers. So letter B, what are all the solutions? You would say, well, we have pi over 3 plus 4 pi n, where n is an integer. And the other one is 5 pi over 3 plus 4 pi n. So again, that's the way I would handle those all solution problems. Simply find the period of the function, and that's what you add on to the solutions, times n, some integer starting at 0. So those are the answers to B. Okay. Now for the rest of the remaining equations that we're solving, we don't have the find all solutions. The rest of the equations and most of the problems that you get from me will involve some type of domain that you can, or range that you need to find the values of. Questions with example 1. Number 2. Here we have cosine 2x equals cosine x over this interval 0 to 2 pi. Let me recopy the equation. Cosine 2x equals cosine x. Here I'm going to need some kind of double angle identity. The cosine of 2x, is that the one where we have 3 options, or is that the one where we only have 1 option? We have 3 options. Now, which one should I use? Folks, you want to keep the number of different type of trig functions to a minimum. So you don't want to be introducing sines or sine squares with this equation. You already have everything in terms of cosine. So let's use the, cosine squared minus 1 is one of my 3 options, right? So let's take out the cosine of 2x, and let's replace that with cosine squared x minus 1. 2 cosine, thank you. 2 cosine squared x minus 1 equals cosine x. And let's get 0 on the right-hand side. Let's subtract cosine x from both sides, giving me 2 cosine squared x minus cosine x minus 1 equals 0. And believe it or not, the left-hand side is a quadratic equation, a factorable quadratic equation in disguise. And if it doesn't jump out at you, use substitution. You can think of cosine x as being u, and this is nothing more than 2u squared minus u minus 1 in disguise. Now it's obvious how we can factor that. 2u times u, and I need a minus 1 and a plus 1. The minus 1 needs to get multiplied by 2u to get negative 2u, and positive 1u give me the negative u in the middle. Yep. Now here's where you would set each factor equal to 0, right, and solve for u, but right now let's go ahead and skip ahead and let's take u out and let's put cosine x back in and set each factor equal to 0. So here we would have 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. Solving those two equations for cosine x, here we would get cosine x is equal to negative 1/2, and down here we would get cosine x is equal to 1. Now we got to find all the angles in radians that satisfy those two equations. Let's start with the easier of the two. The bottom one, right? What angle has a cosine of 1? Not everybody at one time, please.
0.
0, right? So we know x is 0. Now how about this one? Well, here we have the cosine of the angle is equal to something negative. So that gives us quadrants 2 and 3. 2 and 3. Got to find our reference angle. Cosine of what angle is 1/2 as a reference angle? That would be 60 degrees, which is pi over 3. So my reference angle in quadrants 2 and 3 end up being pi over 3. So here I am at pi, which we would be thinking is 3 pi over 3, minus pi over 3 is 2 pi over 3. So there's my quadrant 2 solution. And again, we start at pi, which is 3 pi over 3. Add pi over 3 gives me 4 pi over 3. And there's my 3 solutions to that equation. Anybody have any questions about this process? I like how the textbook labels these examples with, here they're saying use a double angle identity. And I like how they're introducing all of the different ways that are going to be available to you. But please understand, right, on the exam, I'm not going to say, psst, you have to use double angle identity to solve this problem. They're going to be all mixed up with one another. Josh, you have a question?
Yeah. Looking at the double angle formula, the one that we used. It's 2 cosine squared a minus 1, which is what it says is equal to 2a. So should cosine of 2a. So should it be cosine of 2x there?
No, because your identity says cosine of 2a is 2 cosine squared a, not 2a.
Okay.
That's why it's x and not 2x there. Does that help?
Yep.
Other questions with this example? Number 3. Now we're with this problem, they want us to answer in degrees. It says here, solving an equation using a multiple angle identity. And let me get you started with the problem, then I'm going to let you continue on with the rest of the problem. We have 4 sine theta cosine theta equals the square root of 3. That almost looks like which identity? Like what's kind of jumping out at you with this problem that looks like one of the identities we've worked with in the last week or so?
Sine times cosine.
No, well,
Sine double angle.
Sine of a double angle. Remember that the sine of 2 theta is 2 sine theta cosine theta, right? We got a 4 sine theta cosine theta. So we can think of the left-hand side of this equation as being 2 times 2 sine theta cosine theta equals the square root of 3. Just looking at it a different way. And then right here sits the sine of 2 theta. So we can take out what's underlined and replace that with 2 times the sine of 2 theta equals the square root of 3. Again, what I have underlined is that part right there. Right? Did I lose anybody? Let's solve this equation for sine of 2 theta. We have the sine of 2 theta equals the square root of 3 over 2, dividing both sides by 2. And the next 2 steps, what you're about to see, will happen in many, many, many problems that you have. Sine of 2 theta, sine of 3 theta, etc. The first thing I like to do is I go up and remind myself about where my answer is supposed to be. Remember what we're doing. We're solving the equation for theta. Theta has to be between 0 and 360 degrees. Here's what I like to do. I say, okay, 0, theta, 360. Which means if I multiply that inequality by 2, 0 times 2 is 0, and we get 2 theta, and we get a 720. So if it means that theta has to be between 0 and 360, 2 theta has to be between 0 and 720. So you and I are going to travel around the unit circle 2 times, right? That's what this is saying. We're going to travel around the unit circle 2 times, and we're going to find all of the angles who has a sine of square root of 3 over 2. And we're going to list all the possibilities for 2 theta. So what can 2 theta be? Well, I'm thinking sine is equal to square root of 3 over 2. What's my reference angle going to be? Square root of 3 over 2. What angle has a sine of root 3 over 2?
60.
60 degrees. There's my reference angle. Now, you and I are going to travel around the unit circle twice. So here we go. Quadrant 1, that's going to be 60 degrees. Sine is positive root 3 over 2, so we're going to stop in quadrant 2, right? So what's the quadrant 2 angle with a 60 degree reference angle? 120. Now, quadrant 3, nope. Quadrant 4, nope, right? Because that's where the sine's negative. Now we're back to quadrant 1 again. 360 degrees, 60 degrees more. 420. And then finally, we're going to stop at quadrant 2 again. So that's like 360 plus 180 minus 60.
480.
480. And then we're done, because we've traveled 2 times around, right? Now, if 2 theta equals these 4 angles, how do we solve for 1 theta? Divide all these by 2. You got it. So theta is 30, 60, 210, or 240. And as you can see, right, all 4 of those is between the original directions. Hey, all 4 of them have to be between these 2 values. There is your solution. Questions there? I like the questions that ask to work in degrees. I like working with degrees better than radians, but what do you do, right?
I just like when they come out neat like that.
All right, I'm going to have you try the next one. The next one, folks, is just like the one we just did, but here you're working with radians. So let's see how you do. What happens? We want to try to, like I said, eliminate the fact we have 2 different trig functions in this equation. We want to try to get it to 1 trig equation. So let's go ahead and subtract secant 3x to the other side, giving us 2 minus secant 3x. Now we'll go ahead and square both sides of the equation. Raise both sides to the 2nd power. Square the left-hand side, all we get is tangent squared, 3x. And on the right-hand side, we're squaring a binomial, squaring 2 terms. So square the first term, multiply the 2 together and double it, and square the last term, we get positive secant squared 3x. Okay. Now on the left-hand side, tangent squared is the same thing as what? Tangent squared is the same thing as your identities. Tangent squared is the same thing as...
Is it 1 minus?
Is it 1 minus, or is it secant squared plus 1?
Secant squared minus 1.
Secant squared minus 1. So this guy right here, we can make secant squared 3x minus 1. I'm just going to recopy the rest of the equation. And what's so nice now is look at that. Secant squared 3x cancels each other out on both sides of the equation. Gone. And now we're down to 1 trig function. So let's get the 4 secant 3x isolated. So I'm going to grab this term, and to make the negative positive, I'm going to pull it to the left-hand side, giving us 4 secant 3x equals, add 1, we get 5. Did I lose anybody so far?
Yep.
You know, I'm not... Go ahead. Where did I lose you?
4 minus 4x secant 3x plus secant 3x. I get that again.
I took this term, brought it over here, made it
I
positive.
don't know. The one below here.
E squared 2 minus secant 3x.
Yeah.
Yeah, I
multiply it out.
square this, square this. This is like the quantity a minus b squared.
Okay. Got it.
You know, up here what happened was we squared that and got a squared minus 2ab plus b squared. What happened there? Okay, let's get secant of 3x isolated. Divide both sides by 4. We have the secant of 3x equals 5/4. Now, I don't like talking in terms of secant. I'd rather talk in terms of sine, cosine, or tangent, right? So we know what? We know that the secant of 3x is the same thing as 1 over cosine 3x. Secant of 3x is the same thing as 1 over cosine 3x. Agree? Now take the reciprocal of both sides of this equation, and we have cosine 3x equals 4/5. Now this tells me, and again you can relate this to our last problem, this 3x tells me that you and I are going to travel around the circle 3 times. What makes this problem different than the last one is 4/5 is not going to give us a nice reference angle. Had that been 1/2 or root 2 over 2 or something like that, then it's a different story. So we need to ask our calculator, what is our reference angle? What angle has a cosine of positive 4/5? So inverse cosine, I gotta make sure I'm in radians, by the way. Mode, I'm in radians. So calculator, what angle has a cosine of 4 divided by 5? And we're going to use 4 decimal places. So that's a 0.6435 radian angle. So we're going to list again, what are all the angles that 3x is allowed to be? Well, we just identified the first one, the quadrant 1 angle, 0.6435. 0.6435. And cosine is positive in quadrants 1 and 4, right? So now we get to find our second angle. We're going to take 2 pi, which is the whole way around, and we're going to subtract off our reference angle of 0.6435, giving us the quadrant 4 angle, 5.6397. 6397. Okay?
You go back to that calculator again?
Sure. Okay. There's the first time around, right? There's the quadrant 1 and the quadrant 4 angle first time around. And now, to get the rest of the 3 x's, let's just take our previous 2 answers and just keep on adding 2 pi. So when I add 2 pi onto this one, that gives me the second time around the one that I'm looking for. So what is 0.6435 plus 2 pi? 4 decimal places, 9267. 6.9267. 6.9267. And now I'll add 2 pi onto this one. So 5.6397 plus 2 pi. 11.9229. 9229. 11.9229. So there's 2 times around. Got to go one more time around. And I'll take the previous 2 answers, add 2 pi onto them. So previous answer, 6.9267 plus 2 pi. 13.2099. And one more 3x angle. We're going to take the 11.929. And we're going to add 2 pi onto that. 18.2061. So there I've denoted with underlines how many times around the circle we've gone. First time around, got our first 2. Second time around, next 2. Third time around, got our last 2. These are all our 3x angles. So like with the last problem, we have to go back and do what now? Take every single one of these and divide by 3. Take every single one of those, divide by 3. I'm going to go ahead and list those answers. But when you take those angles, divide by 3, we get first one, 0.2145 in radians. Next angle, 1.88. Next angle, 2.309. 3.974. 4.403. And finally, 6.069. And all of those, right? All of those are between 0 and 2 pi. Questions there? You can see why I gave you a lot of space for that problem. All right. Moving on. The last technique that we have for solving trig equations is to use our inverse trig functions from our last class. Meaning that you're going to actually take the arc sine of both sides of the equation, or take the inverse tangent of both sides of the equation.